Hi everybody. We are going to start off our next section in chapter 16, 16.2. This is broken up into two parts. I just wanted to do the intro on our next, integral setup, and then later we'll come back and actually do some examples involving that new kind of integral. Now, I'd mentioned to y'all a ways before that we are going to be developing all kinds of new kinds of integrals in this section. Line integrals, okay, like I mentioned here, these are just one of the kinds of integrals that we are going to run into. Now, before I actually touch on those, I want to motivate why I might need a new kind of integral. Why weren't double integrals and triple integrals enough? What new junk do I have to work on? Well, a lot of our problems are actually going to be motivated by concepts in physics. Now, the one that I wanted to focus on today that we will come back to later is work. Okay, if you took physics in high school, you probably ran into a situation where you were computing work based off of forces and distances that usually gave you in those introductory courses just constant situations, right? Constant force, linear distance, so you're applying this force across a straight line path. If you're trying to compute work in that situation, you just multiply stuff, right? Work is force times distance. Is probably what you heard in those earlier classes when you're dealing with constant force and, linear path. Now, it gets a little bit trickier if you're not in that situation, and honestly, in a three-dimensional world, how often do we always run into that? So sometimes maybe we don't have constant forces. What if my force is still applied in a linear direction, but it isn't constant? Well, we solve this using integration. If you take in a physics course at the collegiate level, maybe you've seen this equation. We are going to get the fact that work is going to be an integral over my interval from a to b of, whatever f of x is with respect to dx. So here, what do I mean by f of x? Okay, this f of x describes my force as a function of position, okay? As a function of position on this interval from A to B. So basically that AB, since I'd suggest we've still got our force applied in a linear direction, I'm suggesting that we use that interval to describe, kind of what length we're applying that force over. Okay, so that's how we're specifying my linear direction. I'm allowing my force to vary though, so force can be a function here. Okay, there's actually, if you wanted to flip back in your textbook, there's a whole section that we don't necessarily always cover in Calculus 2 here, where you can actually use integrals of this setup to compute non-constant forces applied across straight lines. Now, where this comes down to why we care, what if my force not only varies as a function of position, but it also isn't applied along a straight line, right? So in the above example, we let force vary, but we are still dealing with straight line paths. That's not necessarily always going to be the case when we live in a three-dimensional world, right? We're not necessarily always going to be applying stuff along straight line paths. Example, if we're in some sort of a gravitational or magnetic field of some sort, your forces don't always go in straight lines in those things. So what we will want to come up with is something kind of similar to the integral we had before. We used integrals to help us solve that problem of non-constant situations. But the catch is that this single variable integral that we had, it's not enough to tackle this problem, okay? So we're going to have to build a new kind of integral to answer this question, and if we come up with that integral, it's really going to have us integrating a vector field along a curve, okay? Now, this is basically one of the reasons we introduced vector fields in the last section, okay? I can express force fields using vector fields. Different locations have different forces associated with them. So that's our function to describe our non-constant force. And then to describe the path, if it's no longer a straight line, maybe we might want to have some sort of curve parameterization to describe the path that we would have to integrate on. So that means we have to come up with a way to integrate a vector field along a curve, and given the tools that we currently have, that might not make a lot of sense. So we're going to start slow. We will build up to this, first starting with just scalar functions. What does it mean, and how can I integrate a scalar function along a curve? We will tackle that first. Okay? Now, to get started, a couple things I wanted to jog your memory on. We'll just try this in the 2D case at first, so I'm not necessarily going to worry too much about the 3D case right now. But in the 2D case, whenever we parameterized a curve, well, we would give a vector function, but this was one that you plug in a single variable and you get a vector back, not multiple things for a vector back. The way that we interpreted that was the single thing that we plugged in was kind of like a time, and then if you plug in that time, it gives you a position on the curve. So this is kind of outlining the path that you would traverse this thing along. You know, you take this collection of times, it spits out a collection of locations, and that collection of locations forms the curve. In either 2D in this case, or 3D if you had maybe another component on the end here. Now, what I'm going to go ahead and do is think about composing this guy with a function of two variables. So I'm still sticking for now in my 2D case, right? Now, what does that actually do? Well, this kind of has the effect that, you know, this two-dimensional input function that I have here, when I go to graph these things, usually we interpreted these as surfaces. Okay, so maybe I have some sort of curve C that I can, you know, think of as having my parameterization. This guy is parameterized by r of t. So what happens when I do my composition here is I can take my points that I get from this curve. You know, you plug in a time, you get a point back on your curve. If you take that point on your curve and you plug it into the function, you are going to get some sort of point on this surface. Now, I can kind of keep repeating this process here, okay, and track what's going on when I plug in each of these points, so that ultimately when I take this composition, I'm going to get some sort of, you know, three-dimensional curve that lies above my original 1 and 2 space. Now the question that I'm going to pose based off of this, you know, composition, you know, we end up getting a, you know, three-dimensional curve back, okay, instead of a 2D one, but it's still got a 2D parameterization. The question I want to ask here is, can I find the area of the curtain? What curtain? Well, I'm going to have you imagine if I just drop kind of a path straight down from this three-dimensional curve to the one that's right below it, you see that I kind of get this sort of wavy looking curtain shape right here. I'm going to ask if we can figure out the area of that thing. Now, if you're like, man, Dr. Wilkinson's really bored, she's trying to find area of these weird shapes, there is, you know, potentially a reason that maybe you might be interested in this. You know, kind of an example that first popped into my mind is if you're thinking about, like, you know, architecture or maybe like 3D printing even. I don't know if you've ever seen like 3D printers work with stuff. If I was interested in trying to print something like, you know, this path that I have up here, 3D printers have to print support material, okay, for pretty much any object that is not immediately supported by stuff underneath it. So either, you know, if you were trying to print this curtain, sure, it would go ahead and do it, but if you just gave it a file that has this thing floating in space, it's gonna have to print some junk under it because, you know, objects don't float, right? You're 3D printer has to print this on top of something. So, maybe I could be worried about how much support material it takes to build this curve. Or, maybe if I was constructing something like this object, like maybe this is supposed to model a roller coaster, and I want to know how much support material I'm going to have to build underneath that, so I can figure out how much materials to order. Finding the area under this thing might be a problem that you actually care to solve. So, if I'm worried about how to find the area of that curtain, I'm going to start by suggesting that we try approximation. What do I mean by that? Well, whenever we've tried to tackle problems like this in class, try to block this up into polygons, right? I'm going to go ahead and think about that bottom curve that I had as approximable by some sort of collection of straight line segments. And this maybe doesn't look like the exact curve I drew above, but hopefully you get the point. If I have this guy approximable as this series of polygons here, maybe trapezoids or rectangles, I basically can try to sum up a bunch of base times height type of situations, right? Sum up base times heights here. Now, if I sum up all of those base times height kind of things, what is this really going to give me? Well, I'm going to go ahead and, label these little bases. We'll call these delta S. We'll see why later. And then these heights, well, where did the heights really come from? The heights really came from, me plugging these points into my surface. So ultimately, I got these by plugging into my function at whatever coordinate that I was interested in, right? So this would be my f of x, y for some appropriate point, right? Let's maybe pick some sort of sample point here. You plug it in, you get a height, okay? Now, what this is really going to look like if you sum up your base times heights, or rather, if you sum up your heights times bases, this is going to look like a bunch of f of x, I, y, I, so a bunch of f of x, y's times delta s, okay, whatever width you picked for each of these rectangles. And you sum all of these from, n equals or I equals 1 to n. Actually, that looks kind of messy. Let me go ahead and clean this up a little bit. So I equals 1 to n. Basically, as many rectangles as you chose to break this up into, that's your n. This I is just an indexing value, okay, that's letting me pick these sample heights. So my sum looks like this thing. What that's going to do in your approximation, we always set this up to imply the existence of some sort of integral that we're trying to compute. What this thing really suggests is some sort of integral that looks like this guy. We are technically integrating along this curve that we started with, that we were trying to approximate with these blocky lines. We are trying to worry about integrating that function that gave us our surface in the first place. And, this delta s on the end, that's really just going to turn into a ds differential. So we have a new differential that we're going to have to work with here. Okay? So this, when I said line integrals was our section header before, okay? This is a line integral, and this is really what I'm having you guys compute whenever I give you a scalar function that you're integrating over some sort of curve. It's kind of like we've got, this curtain that we're trying to figure out here. And it is possible to get negative values back for this. This is a signed area thing as usual. If your surface dips below the xy plane, maybe you might get negative areas for bits of your curtain. But at any rate, this is what a line integral is. How do I compute this, right? How do I actually turn this into something that I can evaluate? Well, here, if I'm worried about trying to figure out this ds sort of situation, evaluating this integral is going to be kind of similar to a lot of the integrals that we've done before. You know, we've got three things we need to fix. We have to fix my bounds because I have no clue how to integrate over a curve. I have to fix my function because, you know, if I'm fixing my bounds, that's probably going to change whatever variables I'm dealing with here. And I'm also going to have to worry about fixing my differential because I sure as heck don't know what to do with ds right now. Okay? Now, some things that I can outline here for how do I evaluate this. We'll go ahead and spell out fixing my bounds and fixing my function. If I want to fix my bounds and my function, these are probably the simpler ones to talk through first. I'm going to use whatever parameterization that I had, use some sort of parameterization, r of t on some interval ab for that curve c. Okay, now what I mean by that is this. Your AB, these are going to be your new bounds. Okay, so whatever interval that you are using to spell out your curve, you know, where does that curve live? What time values are we using to denote where our curve starts and stops? That's where our new bounds come from. And as far as fixing my function, well, you know, r of t, what I want to do is plug this into your f to fix your function, Okay, the reason that I say that is this. If I'm suggesting that we've got numerical bounds as new bounds, this is going to hopefully turn into a single variable integral, but f is not single variable right now. However, if you've got x components and y components for your parameterization, plug the x component in for x and the y component in for y, and then everything turns into a function of t. So then that'll make sense as a single variable integral. The only catch is, what am I doing with this ds? You know, how do I fix that thing? So as far as fixing my bounds go, what this ds is supposed to stand for, the standard convention for, you know, why I called these things s, ds is the arc length differential, and we actually did something very similar to this in the arc length section. If I try to come up with this little arc length between points here, well, I can estimate using a right triangle and some other, you know, changes in y and change in x here. You know, my approximation is going to be that my delta s looks like what happens if I take delta x squared, add it to delta y squared, and then square root the whole damn thing. Now, this doesn't help me necessarily, because if I straight just tried to turn this into differentials, that's going to suggest that ds is the square root of, you know, dx squared plus yada yada. We don't want our differential stuck inside of a function. I don't know how to handle that. So we're going to manipulate this the same way that we did in the arc length section. Now, the trick that we used there is I made use of the fact that we're trying to convert this over to t. So I'm going to throw some changes in here that ultimately will cancel each other out. Namely, if I divide everything inside of this square root through by delta t quantity squared, well, a division of everything, by delta t quantity squared, this guy was in the wrong place, means that when it's inside of the root, it's like I divided everything through by delta t. So I can offset this by just multiplying by delta t on the outside. All of that cancels. Now, as far as my differential estimate is concerned, what this suggests is that ds, since all these things are equal, ds is really going to look like x prime of t quantity squared plus y prime of t quantity squared times dt. Or the simpler way for me to, think about writing this is the same exact thing as, if I was taking a magnitude of x prime of t, y prime of t, okay, in a vector. Or the shorthand for this is really the derivative of whatever the heck your parameterization was. So this is your conversion factor for your differential right here. Whatever parameterization that you chose, derive it, take a magnitude, slap a dt on the end, and you're good. Okay, so what this is going to tell me, if you didn't care about any of the derivations before, if you just want a way to crank out these integrals, how do I rewrite stuff? This is where we need to tune back in. If you've got a continuous function and a smooth curve that you are trying to integrate over, you need a parameterization for that curve on some interval. And once you have that, we've now got a way to rewrite my bounds, my function, and my differential. And the way that we do it is this. I had mentioned before, if we wanted to fix my bounds, okay, your bounds are now going to be AB, whatever that is from your parameterization that you picked. Fixing your function, the way that we fixed the function was, you will notice I took my curve that, parameterized my C, and I just plugged it straight into F. Okay, so here, basically compose F with your parameterization to fix your function. And then the final thing that we want to note is, if I wanted to fix my bounds, this arc length differential, this always, always, always equals the magnitude of r prime of t dt. So whatever parameterization you chose, you have to derive it, take the magnitude of it, and then slap a dt on the end. Okay? So same deal as before, we just have to worry about fixed bounds, fixed function, fixed differential, and now we have a way that we can do it. Okay? And a comment before I go ahead and move on. If you're worried about the fact that I only treated the 2D case and not the 3D case, the 2D case is just nicer to draw the pictures for. The formula still holds the same. Okay? So just in case you were worried, okay, same thing for 3D as it is for 2D. We still take a derivative of our parameterization, take the magnitude, and slap a dt on the end. Okay? And then the final comment that I'm going to make before we run off here, I've mentioned for a lot of the previous integrals that we've dealt with, if you're worried about measuring something, integrate one with respect to the appropriate differential. This is the same case here. When I kept making reference to doing things similar to our arc length section, this is basically the same setup for that arc length formula. So if you do, perchance maybe just check it out. If you set up an integral of 1 along a curve with respect to arc length, and you come up with a parameterization, give it a try. You will get precisely the arc length formula from section 13.3, okay? Because the arc length formula there, all it has you integrate is just this thing over an appropriate interval. Please check out next video for examples on this.